From liquids that crawl up walls to metals that melt in your hand, the world is full of substances that ignore the rules of reality. Today, I'm counting down 20 of the most unusual substances in the world. Starting with number 20, the liquid that acts like a magnet. Ferrofluid. It looks like something out of science fiction. It's a black liquid that looks alive, it forms sharp spikes and moves in response to magnets, but it is completely real and the result of clever materials science. Ferrofluid is made by suspending tiny iron oxide particles, only about 10 nanometers wide, in a carrier liquid like oil or water. The particles are coated with a surfactant to prevent them from clumping together, and when exposed to a magnetic field, the particles align along the magnetic field lines, creating this spiked pattern that seems to move and breathe. It was invented in 1963 by NASA engineer Steve Papel, who was trying to develop a liquid fuel that could be controlled in zero gravity using magnets. Although it never made it into rocket systems, the material found uses in entirely different areas. Today it's used in hard drives to dampen vibrations and sealing moving parts, in loudspeakers to reduce friction and improve the sound quality, and even in art installations and fashion. Scientists are continuing to study ferrofluids for advanced applications like targeted drug delivery, cooling for electronics, which would be good, and adaptive optics. In medicine, researchers are exploring the possibilities of using these magnetic fields to steer ferrofluids through the bloodstream to deliver medicine directly to tumors. However, this is still experimental and requires overcoming challenges like toxicity and biocompatibility. But visually, they still are one of the most mesmerizing substances. Under a magnet, it looks almost alive. It forms these fractal peaks and valleys that change in real time, and despite its simplicity, it behaves in ways that challenge our own intuition. Number 19, the lightest solid on Earth. Aerogel is often called frozen smoke because it does kind of look like a puff of vapor you can hold in your hand. It is an ultralight solid made by replacing the liquid component of a gel with a gas without collapsing the gel structure. The result is a material that's up to 99.8% air by volume, yet solid enough to hold in your palm. The process to make it was invented in 1931 by Samuel Kistler, who made a bet that he could replace the liquid inside a gel without causing it to shrink. He did it using a process called supercritical drying, which removes the liquid under high temperature and pressure so the surface tension doesn't collapse the gel's network of silica. What's left is a ghostly porous structure that's incredibly light but surprisingly strong for its density. A typical silica aerogel weighs only about 0.003 grams per cubic centimeter. That's 15 times lighter than styrofoam, yet it can support many times its own weight. It also is an outstanding insulator. It's capable of withstanding direct contact with flame on one side while keeping the other side cool enough to touch. NASA's been using aerogel aboard the Mars rover and the Stardust missions, where it captured microscopic comet particles traveling at extreme speeds. Despite its delicate appearance, though, aerogel isn't fragile in all forms. Flexible polymer-based versions are being developed for clothing and spacecraft insulation, but one of its strangest features is how it distorts light. Because of its low density, aerogel bends and scatters light in a way that does make it look semi-transparent and almost unreal. But it is entirely real, and it's one of the most efficient thermal insulators ever made. From NASA laboratories to architectural insulation, aerogel is one of the most extraordinary and genuinely weird substances on Earth. Nearly weightless, barely visible, yet capable of standing up to fire and freezing temperatures alike. Number 18. The darkest material ever made. Vantablack. It's so dark that when light hits it, almost none of the light bounces back. It absorbs up to 99.965% of any visible light, making the object coated in it look like a black void, as if space itself had been poured over the surface. It was developed in 2014 by Surrey Nanosystems in the UK. Vantablack's name stands for Vertically Aligned Nanotube Arrays. It's made from millions of tiny carbon nanotubes, each about 3,500 times smaller than the diameter of a human hair, grown on a surface so densely that light entering the structure gets trapped in it and repeatedly absorbed rather than reflected. Unlike paint, Vantablack isn't brushed or sprayed on. It's created through a process called chemical vapor deposition, where the carbon nanotubes will grow directly from a substrate in a high-temperature chamber. Each nanotube is like a microscopic straw that captures incoming light, and it bounces it internally until virtually none of it escapes. That's what gives it that eerie, depthless appearance. Objects will lose their shape, look completely flat even when they have curves or texture. Originally, it was developed for aerospace and defense applications like minimizing any stray light inside telescopes and improving the performance of optical instruments. It's also used in infrared cameras and certain satellite sensors where light absorption is critical. However, it also did spark controversy in the art world. In 2016, British artist Anish Kapoor required the exclusive rights to use it for artistic purposes, which led to a public backlash among other artists who felt that no one should own a color or material. This inspired others to develop competing ultra-black materials. Some, like MIT's 2019 version, are even darker, absorbing up to 99.995% of light. Well, despite its impressive darkness, Vantablack has limitations. It's not suitable for all surfaces and can be damaged by physical contact. The material does require specific conditions to be applied safely. Still though, it does remain one of the most scientifically remarkable substances ever engineered, a near-perfect absorber that gives form to the concept of absolute blackness. Number 17. Liquids that act like solids. At first glance, a non-Newtonian fluid looks ordinary, like water or paint, but under stress it behaves completely in unexpected ways. Push it gently and it flows like a liquid. Strike it hard and it suddenly turns solid. These strange materials defy Isaac Newton's classic definition of viscosity, where a fluid's resistance to flow stays constant regardless of the applied force. A classic example of this is a mixture of cornstarch and water, often called Oobleck. When you slowly dip your hand into it, it yields easy, but if you punch it, it resists, feeling as firm as rubber. This behavior comes from the suspension of solid particles in the liquid. Under sudden impact, the particles will jam together and increase viscosity and form a temporary solid network. Once the stress is removed, the structure collapses and the mixture flows again. Now, non-Newtonian behavior isn't really limited to kitchen experiments. Many everyday substances like ketchup, toothpaste, and paint have similar effects. Ketchup, for instance, becomes less viscous when shaken or squeezed, which is why it finally pours out after you hit the bottle. Engineers exploit properties like this in some surprising ways. Non-Newtonian fluids are used in body armor, athletic gear, and even protective coatings. Materials like D3O, a polymer-based non-Newtonian compound, remain flexible during normal movement, but they harden instantly upon impact, helping absorb shocks and reducing injuries. But what makes them truly weird is the unpredictability of them. They don't often obey simple rules for liquids and solids. Instead, they sort of exist in a gray zone between both. Their ability to transition between states depending on the stress, speed, or pressure reveals how complex the physics of seemingly ordinary materials can be. Number 16. The metal that melts in your hand. Gallium is a very strange metal. At room temperature, it looks solid and silvery, similar to aluminum. But if you pick it up, it quickly begins to melt in your palm. That's because gallium's melting point is just 29.7 degrees Celsius. That's about 85.5 degrees Fahrenheit. It's slightly below the average human body temperature, and within a minute or two, it turns into a silvery liquid that can be poured like mercury, though unlike mercury, gallium is not toxic and way safer to handle. First isolated in 1875, gallium's discovery helped confirm the predictive power of Dmitry Mendelev's periodic table. Mendeleev had theorized the existence of an element with properties between aluminum and indium, what he called eka-aluminum, and gallium matched these predictions perfectly. Now, gallium's physical properties make it valuable. It can wet and adhere to glass, ceramics, and metals, which makes it useful in mirrors and optical devices. When alloyed with other metals, gallium can form compounds that stay liquid well below room temperature. That's useful in cooling systems and specialized thermometers. Gallium arsenide and gallium nitride are semiconductors that power high-frequency transistors, LEDs, and even some of the most advanced radar systems and smartphone chips. It expands when solidifying, which is rare for a metal, meaning that if you freeze it inside a container, it will shatter the walls of it. Scientists use it in research to mimic liquid mercury without the toxicity and to explore metallic bonding at low temperatures. Watching it melt in your hand, though, kind of feels surreal, like science fiction brought to life. It's completely real, and an element that bridges the gap between solid and liquid with ease. In a world of rigid metals, gallium stands apart. It's a metal that refuses to stay solid when touched. Number 15. The slipperiest substance ever discovered. Teflon, or polytetrafluoroethylene, PTFE, is so slippery that nearly nothing sticks to it, not even a gecko or a piece of tape. It's a synthetic polymer made entirely of carbon and fluorine atoms, forming one of the strongest chemical bonds that is known. The structure gives it exceptional non-stick and heat-resistant and chemical-resistant properties. It was invented accidentally in 1938 by chemist Roy Plunkett and DuPont. Teflon was originally discovered when he opened a gas cylinder of tetrafluoroethylene and found a white waxy solid inside. Turned out that the gas had polymerized on its own, forming a completely new material. The molecular structure is the key to its strangeness. Each carbon atom in the chain is surrounded by fluorine atoms, which shield it from almost any chemical reaction. The result is an extremely inert surface, so much so that even insects or bacteria can't adhere to it. It's non-reactive, non-conductive, and can withstand temperatures around 500 degrees Fahrenheit, that's 260 Celsius. And while most people know it from non-stick cookware, Teflon's uses extend well beyond the kitchen. Its use in aerospace wiring, medical implants, seals, and gaskets that must resist extreme environments. NASA uses PTFE coatings to protect spacecraft components from radiation and chemical degradation. In the chemical industry, pipes and containers are often lined with Teflon to prevent corrosion from highly reactive acids. In terms of friction, Teflon's coefficient is among the lowest of any known solid, around 0.04. That means it's smoother than ice and one of the best lubricants in existence. Its ability to repel both water and oil makes it a cornerstone in countless technology. However, Teflon's production history has raised environmental concerns. For decades, a compound called PFOA, used in manufacturing, has contaminated water supplies and was linked to health risks. Modern PTFE production has largely phased out PFOA, but the controversy served as a reminder that even revolutionary materials can have unintended consequences. In every sense, it's the ultimate example of smooth science. Number 14. The liquid you can run on. Oobleck, we mentioned that before. It's a simple mixture of cornstarch and water, but its behavior is anything but simple. This everyday combination forms what scientists call a shear thickening fluid. This is a material that changes from liquid to solid depending on the amount of force applied to it. Move through it slowly and it flows like a thick liquid. Hit it hard or step on it quickly and it stiffens instantly, allowing you to stand or even run across its surface for a brief moment. Oobleck itself is a suspension, meaning solid particles like cornstarch are dispersed throughout a liquid, water, without dissolving. When left undisturbed, the particles have room to move past one another so the mixture flows freely. But under sudden stress, those particles are forced tightly together, forming a temporary solid network. When the pressure is released, they separate again, returning to the mixture in liquid state. Military and engineering has explored using shear thickening fluids in flexible body armor, and when struck, the material instantly hardens and distributes the force across a wider area and provides protection without sacrificing its mobility. Even beyond defense, the concept applies to fields like robotics, impact-resistant clothing, and vibration dampening. It is also used in teaching physics because it shows non-Newtonian behavior so clearly. It shows how some fluids defy the standard laws of motion and viscosity described by Isaac Newton. Oobleck gets its name, though, from a 1949 Dr. Seuss book, Bartholomew and the Oobleck, where a sticky green goo falls from the sky. The real version may not rain down from the clouds, but it is still mesmerizing to see in person. People often fill swimming pools or tanks with it for demonstrations, running across it before it liquefies beneath them. It's a great example of how strange behavior can come from simple ingredients. Number 13. The lightest material ever created. Graphene aerogel is so light it can rest on a flower petal or the fluff of a dandelion without bending it. It's made from a 3D network of graphene, single-atom thick sheets of carbon. It is considered the lightest solid ever made, with a density as low as 0.16 milligrams per cubic centimeter. It's about 7 times lighter than air. It was developed in 2013 by researchers in China. Graphene aerogel combines the strength and conductivity of graphene with the sponge-like structure of aerogel. To make it, scientists create a gel containing graphene oxide, then remove the liquid using freeze drying. This leaves behind a porous solid composed almost entirely of air. Despite being incredibly light, though, the aerogel can absorb up to 900 times its own weight in oil and return to its original shape after compression. This makes it valuable for environmental cleanup, especially oil spills, since it can soak up pollutants efficiently and be reused many times. The structure of it also makes it a promising material for energy storage, filtration, and even sound insulation. Visually, graphene aerogel looks like a dark, fragile sponge, but it's way tougher than it looks. When pressed, it springs back almost completely, showing a kind of memory for its original shape. It's also resistant to extreme temperatures, and it's chemically stable in any harsh environments. Though still expensive and limited in large-scale production, graphene aerogel represents the cutting edge of materials science. It's a structure lighter than air, yet strong enough to support thousands of times its own weight. It might be a glimpse into a future where the boundaries between solid and gas become thinner than a single atom, proving that the weirdest substances sometimes emerge not from nature, but from human ingenuity that push matter to its limits. Number 12. The mystery material that could withstand extreme heat. Starlite. It's one of the most mysterious substances ever revealed to the public, mainly because no one outside a small circle ever knew exactly what it was made of. Created in the late 1980s by British hairdresser and amateur chemist Maurice Ward, Starlite was a white, putty-like material that could allegedly resist temperatures of up to 18,000 degrees Fahrenheit, that's 10,000 degrees Celsius. In live demonstrations on British television, it was shown protecting an egg from a blowtorch so hot that the metal melted nearby. When the flame was removed, the egg was cool enough to the touch, unharmed beneath a thin layer of charred starlight. Tests carried out in independent labs, including some of the UK Ministries of Defence and NASA, confirmed that the material had remarkable thermal resistance. It didn't ignite, it didn't produce toxic fumes, and withstood levels of heat that should have destroyed almost anything organic. The science behind its performance has never been fully explained because Ward refused to reveal the formula. He feared losing control of his invention or being taken advantage of by corporations. Starlite reportedly contained a mixture of polymers, ceramics, and other organic compounds, and the secret likely lay in how it expanded under the heat, creating a char layer that insulated and reflected thermal energy away. That process, called intumescence, is used in some modern fireproof coatings, but nothing demonstrated quite the level of protection that Starlite did. After Ward's death in 2011, his family inherited the formula, but it's unclear if it was ever formally documented. No verified samples are known to exist today, and scientists still debate whether the exact material could ever be reproduced. Whether it's an overlooked breakthrough or simply lost to time, Starlite does remain one of the weirdest materials ever demonstrated. It has entered scientific legend as a rare example of a world-changing substance that has vanished with its inventor. Number 11. The powder that becomes gel on contact with water. Sodium polyacrylate might not look impressive at first. It's just a fine white powder used in everyday items like diapers and instant snow toys. But this synthetic polymer can absorb up to 300 times its own weight in water, turning from a dry grain into a soft jelly-like substance almost instantly. The transformation happens because each molecule contains repeating chains of sodium acrylate units that attract and trap water molecules through hydrogen bonding and ion exchange. When water touches it, the polymer chains unwind and create a massive surface area that locks in the liquid. The result is a gel so stable it won't easily release moisture even when squeezed. This property makes it invaluable in products designed to hold or control fluids, like absorbent pads, spill cleanup materials, and horticultural gels that keep soil moist. In chemistry terms, sodium polyacrylate is a superabsorbent polymer. It was first developed in the 1960s by the U.S. Department of Agriculture, originally as a soil additive to help retain water in arid environments. However, its biggest commercial success came decades later with disposable diapers and sanitary products. Its ability to trap water efficiently while staying dry to the touch changed the hygiene industry permanently. Its structure also gives it unusual chemical behavior. When salt water is added, the polymer's ability to absorb liquid drops dramatically. This happens because the sodium ions in the salt interfere with the electric charges along the polymer chain, reducing the capacity to attract any water. This is why it works so much better with fresh water than seawater. In classrooms, it's often used for science demonstrations that look magical, pouring a few drops of water onto a tiny pile of powder that instantly swells into a mound of clear gel. It is a simple material, but its ability to transform its state so dramatically with just a drop of water does make it one of the strangest and most useful substances humans have ever made. Number 10. The substance between solid and liquid. Liquid crystals. They're one of the strangest classes of materials. They exist in a state between solid and liquid, and they flow like a liquid but maintain some of the orderly molecular structure of a crystal. This sort of in-between condition gives them amazing optical properties, which humans have learned to harness in displays, sensors, and other devices. This phenomenon of liquid crystals was first discovered in 1888 by Austrian botanist Friedrich Renitzer, who was studying cholesterol derivatives. He noticed something unexpected. When he heated certain organic compounds, they didn't melt directly into a clear liquid. Instead, they formed a cloudy, viscous phase that behaved partly like a solid crystal and partly like a fluid. This new mesophase, as scientists later called it, defied classical definitions of matter. In an ordinary liquid, molecules move randomly in every direction. In a solid crystal, molecules are rigidly aligned and in a repeating lattice. But in a liquid crystal, the molecules can move freely like a liquid while still maintaining a general orientation. This orientation can shift when subjected to temperature changes, pressure, or even electric fields, causing the material to change color or transparency. It's this sensitivity is what makes LCD displays possible. An LCD screen, each pixel contains liquid crystal molecules sandwiched between layers of glass and polarized filters. When an electric current passes through, the crystals twist and realign, controlling how much light can pass through. And one pretty cool thing is they can also happen naturally, even inside the human body. The cell membranes that make up tissue have liquid crystalline phases, which help regulate structure and flexibility. Many biological molecules, like DNA and certain proteins, also show these kinds of properties. Despite being invisible to most people, liquid crystals form the backbone of modern display technology. They occupy a strange middle ground in the physical world, neither truly solid nor liquid, yet essential to how we see and interact with information every day. Number 8. Plastics that repair themselves. Imagine a plastic phone case that would mend a scratch overnight, or a car bumper that heals after an impact. That's the promise of self-healing polymers. These remarkable substances mimic biological healing. They use built-in chemical reaction to close wounds in the molecular structure. This concept first gained traction in the early 2000s when researchers at the University of Illinois developed a polymer embedded with tiny capsules of healing agents. When the material cracked, the capsules broke open and released a liquid resin that filled the gap and solidified. Since then, scientists have refined the concept, creating self-healing materials that can fix themselves repeatedly, sometimes within seconds. Capsule-based systems do rely on microcapsules that rupture upon damage, and intrinsic systems, on the other hand, use reversible chemical bonds that can break and reform when triggered by heat, light, or even just contact with air or moisture. One breakthrough came from researchers in Japan who created a transparent polymer that could heal simply by being pressed together at room temperature, no heat or catalyst required. Another team at the University of California developed a stretchable electronic polymer that could conduct electricity and heal both its structure and functionality. But beyond consumer products, self-healing materials have potentials in aerospace, construction, and medical devices. Airplane wings and spacecraft coatings that can automatically repair small cracks could dramatically improve safety. In infrastructure, concrete infused with self-healing polymers or bacteria-based systems could extend the lifespan of bridges and tunnels by decades. These self-healing polymers are redefining how we think about durability. They do blur the line between inert matter and a living system, and they hint at a future where our devices, buildings, and vehicles will quietly take care of themselves, no glue, tools, or repairs required. Number 7. The liquid that defies gravity. Superfluid helium. It's one of the strangest substances we know of. When helium is cooled to just a few degrees above absolute zero, that's negative 273 degrees Celsius, it undergoes a transformation that breaks the normal rules of physics. It becomes what's known as a superfluid, a state of matter with zero viscosity, zero friction, and the ability to flow without resistance. In this state, it can climb up and out of its container, drip through solid materials, and even form perpetual motion-like currents that never slow down. There are two main isotopes of helium, helium-4 and helium-3. Both can enter the superfluid state under extreme cold, though at slightly different temperatures. The effect was first observed in 1937. Scientists noted that when helium-4 was cooled below 2.1 degrees Kelvin, it suddenly lost all internal friction and began to behave like a completely new form of liquid. The key lies in quantum mechanics. In a superfluid, all helium atoms condense into the same quantum state, behaving collectively as a single superatom. This phenomenon, called Bose-Einstein Condensation, allows the atoms to move in a perfect synchrony without colliding or creating turbulence. When superfluid helium is placed in a container, it exhibits other weird effects. It can form a thin film of sorts that creeps up and over the sides, flowing continuously until the container empties itself. It also conducts heat in an extraordinarily efficient way, so much so that temperature differences inside it vanish almost instantly. But superfluid helium has no practical use outside of low-temperature physics, but it is invaluable for research. Studying it helps physicists understand quantum phenomena on a macroscopic scale. To the naked eye, superfluid helium just looks like an ordinary liquid, but its behavior is beyond anything seen in nature. It's not just weird, it's one of the purest glimpses humanity has into the quantum world that underlies reality itself. Number 6. The solid metal made from the simplest element. For decades, scientists theorized that under extreme pressure, hydrogen, the lightest and most abundant element in the universe, could transform into a metal. It would conduct electricity, reflect light like aluminum, and possibly even remain stable after the pressure was released. But turning hydrogen into metal required conditions so extreme that, for most of history, it remained purely theoretical. Hydrogen gas normally exists as pairs of atoms, H2, forming a colorless, non-metallic gas. However, in 1935, physicists Eugene Wigner and Hillard Bell Huntington proposed that if enough pressure were applied, far greater than what exists at the Earth's core, the molecules would break apart and the atoms would arrange into a crystalline metallic lattice. This prediction sparked one of the longest-running quests in high-pressure physics. That is, until 2017, then a Harvard research team led by Isaac Silvera and Ragnar Dias announced that they had finally created metallic hydrogen inside a diamond anvil cell. By squeezing a microscopic sample of hydrogen between two diamond tips to pressures above 400 gigapascals, that's about 4 million times Earth's atmospheric pressure, they claimed the gas turned reflective, suggesting it had become metallic. However, the results are controversial. The sample was destroyed during testing, and other labs have not yet reproduced it conclusively. If metallic hydrogen truly exists, it would be one of the weirdest and most valuable materials imaginable. Theoretically, it could be a room-temperature superconductor, meaning it could conduct electricity with zero resistance. This would revolutionize energy transmission, magnetic levitation, and electronics. Even more tantalizing is its potential as a rocket fuel, because of its extremely high energy density, metallic hydrogen could provide twice the thrust of conventional fuels. But the challenges are immense. Creating and stabilizing it requires pressure so high that no container on Earth could hold it for long. Some scientists believe that if released, metallic hydrogen might revert explosively to its molecular form, releasing huge energies. Others think a metastable version might survive at normal pressure, but this remains unproven. Whether it truly exists in a stable, reproducible form is uncertain, but if confirmed, it could be the single most extraordinary material ever synthesized by humans. Number 5. Liquid that hardens on impact. Dilatant fluids. They're also known as shear thickening fluids. These are materials that behave like a liquid under gentle movement, but instantly harden when struck. They're closely related to non-Newtonian fluids like Oobleck, but engineered for practical use, especially in body armor and protective equipment. These fluids consist of solid particles, typically silica, that's suspended in a liquid like polyethylene glycol. When the suspension is at rest or under slow movement, the particles are free to move past one another and the fluid flows easily. But when struck with any force, the particles collide and lock together, forming a temporary solid that resists motion. Traditional body armor uses rigid plates or woven fibers like Kevlar, which can restrict your movement and add bulk, and in contrast, these fabrics impregnated with shear thickening fluids remain soft and flexible. But they instantly stiffen to absorb and distribute the energy of a bullet or a blade strike. This technology gained attention in the early 2000s when researchers at the U.S. Army Research Laboratory and the University of Delaware demonstrated fluid-infused Kevlar that could stop projectiles more efficiently than standard armor. Commercial versions using proprietary blends like D3O are now found in everything from ski helmets to phone cases. They can look and feel like a simple gel, but they transform into something nearly solid in milliseconds. These dilatant fluids blur the boundary between solid and liquids, showing how motion itself can define a material's properties. Number 4. The real-life invisible metal. Transparent aluminum? Well, it sounds like something from science fiction, and it actually is. The term first appeared in Star Trek IV: The Voyage Home from 1986, where the crew used it to build a transparent tank that was strong enough to hold 2 whales. Decades later, scientists actually made it, though under a different name, aluminum oxynitride, or ALON. ALON is a ceramic material composed of aluminum, oxygen, and nitrogen. Now, what makes it cool is that it combines optical transparency with the strength of a metal. It's a solid crystalline material that can transmit light from the ultraviolet through the mid-infrared spectrum while withstanding tremendous force. Originally developed by the U.S. Air Force and Raytheon in the 1980s, ALON was first intended for use on military armor and across aerospace applications. Unlike ordinary glass, which shatters when struck, ALON can withstand bullets and explosions. It's used today in bulletproof windows, domes for sensors and armored vehicle canopies, and one plate of ALON, just 1.5 inches thick, can stop a .50 caliber bullet while offering clearer optical performance than traditional laminated bulletproof glass, which typically needs to be over 3 inches thick. Producing it is a complex process. It starts like a fine powder that's pressed into shape and then sintered at temperatures that exceed 3,600 degrees Fahrenheit to form a transparent solid. The process has to be tightly controlled, and once polished, the result looks like ordinary glass, but it is tougher than steel, scratch-resistant, and impervious to most acids. Although it's more expensive than conventional glass, improvements in manufacturing are lowering the costs, making it viable for commercial use. It is one of the most tangible examples of science fiction becoming a science fact, a material you can see through but almost can't break. In the hierarchy of weird substances, few are as real-world practical and visually striking as aluminum oxynitride. Number 3. The ice that grows like a living thing. Among the strangest natural substances on the Earth is aeromorphous ice. This is more commonly known as hoarfrost or frost flowers. But at the microscopic level, it's something extraordinary. Unlike compact hexagonal ice we're familiar with in cubes or glaciers, aeromorphous ice forms complex feathery structures that seem to grow outwards into the air. This form of ice develops under very specific conditions, when humid air comes into contact with a surface that's below freezing, but with minimal wind. As water vapor touches the cold surface, it instantly crystallizes, forming these delicate spires and dendrites. The result is a lightweight porous structure that resembles white coral or frozen lace. It's not created from liquid water that freezes like typical ice, but directly from vapor turning into a solid, a process called deposition. This means it bypasses the liquid phase entirely, and under the right conditions it can even grow several centimeters per hour. In the Arctic and Antarctic, a related formation called frost flowers appears on the surface of new sea ice. These are clusters of ice crystals that form when supercooled air meets the brine-saturated surface. These frost flowers aren't just visually cool, they also play a role in atmospheric chemistry. They can release salt and other compounds into the air, which affects local weather. Because of their delicate nature, the aeromorphous ice structures are hard to study. Even the warmth from a human hand can destroy them, but scientists have used high-speed photography and microscopy to examine the formation of them, revealing insights into how phase changes in water can produce cool geometries. No matter how many times scientists observe it, the growth of frost flowers and their otherworldly shapes remain among the weirdest but coolest behaviors of any common substance on Earth. Number 2. Matter at the edge of reality. The Bose-Einstein Condensate. It's not just one of the weirdest substances known to science, it's arguably the strangest form of matter that humans have ever created. It sits at the boundary between the quantum and classical worlds, where atoms stop behaving like individual particles and start acting like one single unified superatom. In this state, matter behaves less like a gas or a liquid and more like pure quantum energy that's made visible. The concept began in the 1920s with Indian physicist Satyendra Nath Bose and his collaborator Albert Einstein. Bose's work on quantum statistics suggested that under extremely low temperatures, certain particles, later called bosons, could occupy the exact same quantum state. Einstein realized that if a gas of bosonic atoms were cooled close to absolute zero, all the atoms would effectively merge into a single quantum entity. This theoretical condensate wouldn't just behave differently, it would be different, existing in a state where quantum mechanics operates on a macroscopic scale. For decades, of course, this only remained a theory. Temperatures low enough to create this simply couldn't be achieved. But that changed in 1995, when scientists Eric Cornell and Carl Wyman at the University of Colorado, and separately Wolfgang Ketterle at MIT, succeeded in producing the first Bose-Einstein condensates using rubidium and sodium atoms. By cooling these gases with laser beams and magnetic traps to just a few billionths of a degree above absolute zero, they caused the atoms to collapse into a single quantum state. The result was astonishing. The cloud of atoms suddenly dimmed, slowed, and began to act as if it were one particle, hundreds of thousands of atoms moving in harmony. But these substances are incredibly fragile. A slight increase in temperature or disturbance from external light can just destroy it. To maintain a condensate, scientists have to isolate it in a near-perfect vacuum, shield it from vibration, and cool it with precision lasers that remove the last traces of atomic motion. In recent years, NASA has created a condensate aboard the ISS. In the microgravity of orbit, condensates can be maintained for longer periods and observed in ways impossible on Earth. These experiments in space could lead to breakthroughs in quantum sensing and navigation. It is the closest thing that we have to seeing the quantum world with the naked eye, a fleeting, ghostly state of matter that flows without resistance, pulses like a single organism, and shows us how strange the universe truly is when you strip away heat, energy, and motion until only pure quantum order remains. Number 1. The strongest and weirdest substance in the universe. If there's one material that defies every rule of ordinary physics, it's nuclear pasta. Found not on Earth, but deep inside the crust of neutron stars, neutron pasta is believed to be the strongest known substance in the universe, so dense, a single teaspoon of it would weigh more than 1 billion tons. Despite the astronomical scale, though, it is a real physical material predicted by the laws of nuclear physics and supported by computational models. To understand nuclear pasta, though, you gotta imagine what happens during the death of a big star. When a star many times larger than our Sun runs out of nuclear fuel, it collapses under its own gravity, crushing the protons and electrons together to form neutrons. The result is a neutron star, an object roughly 20 kilometers wide, but with more mass than the Sun, packed so tightly that the atomic nuclei themselves are forced into exotic arrangements. At these extreme densities, around 10 to the 14th grams per cubic centimeter, the forces inside matter stop behaving as they do anywhere else. Neutrons and protons, normally confined within the atomic nuclei, are squeezed so close that their interactions create patterns resembling complex structures. Nuclear physicists using quantum simulations discovered that these patterns resemble the shapes of pasta, lasagna-like sheets, spaghetti-like strands, and gnocchi-like clumps, hence the name nuclear pasta. According to simulations, this pasta has astonishing mechanical properties. Its shear strength, the measure of how much force it can withstand before deforming, is estimated to be 10 billion times greater than that of steel. The crust of a neutron star is composed largely of this nuclear pasta, and it's so tough it can store enormous amounts of stress, which may explain these sudden star quakes and glitches that are observed in pulsars, which are rapidly rotating neutron stars that emit beams of radiation. The weirdness doesn't stop there. This nuclear pasta isn't just strong, it's electrically conductive and possibly magnetically ordered. It may affect how heat and magnetic fields move through neutron stars, influencing the behavior of their crust and magnetic poles. No human has ever touched, seen, or produced nuclear pasta, but its existence is inferred from astrophysical data and computer models. In 2018, researchers using supercomputers at Indiana University and Los Alamos National Lab ran detailed simulations that confirmed how these pasta-like structures form, and they estimated their breaking strength. Their conclusion: nuclear pasta is quite possibly the strongest material in the cosmos. To picture it is nearly impossible. Imagine a region of gravity where it's so intense that a pebble would fall towards the surface at 1/10 of the speed of light. Inside, the crust is not made of rock or iron, but of neutron-rich matter packed so tightly that an atomic nucleus, it twists itself into filament sheets and bubbles that are shaped by forces we can barely model. In a sense, this nuclear pasta represents the ultimate extreme of matter's weirdness. It is a place where ordinary structures of atoms break down, and nature just reorganizes itself into patterns that are beautiful and terrifying. We can't bring a sample of it back to Earth, but in the glow of the distant pulsars, we can see its effects: ripples in space-time, flashes of radiation, and signatures in the cosmic background that remind us that somewhere out there, in the frozen heart of a dead star, the universe is cooking its own strange and indestructible version of humble pasta.